transforms the chemical energy in fuel to mechanical energy. Diesel engines, which have been serving mankind for over a century, are the most versatile and economical IC engines. To release the chemical energy in diesel effectively, an atomized form of the fuel is made to contact with high temperature and high pressure air. This energy is effectively transferred as mechanical rotational energy. So the operation of a diesel engine is all about producing high temperature and high pressure air continuously. We will see how this is achieved in this video. Piston, connecting rod, crank, and cylinder form a mechanism called slider crank mechanism. Here, the linear motion of the piston is transformed to a rotary motion at the crank. In an IC engine, this mechanism is properly supported in an engine block. Cylinder head, valves, and fuel injector are fitted above the engine block. When the piston moves downwards, inlet valves open and fresh air from outside is sucked in, or, in other words, the engine breathes. During the return stroke, inlet and exhaust valves are closed, and the air inside the cylinder gets compressed. During the compression stroke, the piston does work on the air, so the temperature and pressure of the air will rise to a level which is higher than the self-ignition value of the diesel. An atomized form of diesel is injected into this compressed air. The fuel gets evaporated and undergoes an uncontrolled spontaneous explosion. As a result, the pressure and temperature rise to high-level values. The high-energy fluid pushes the piston downwards. The hot air does work on the piston, and energy in the fluid is converted to the mechanical energy of the piston. This is the only stroke where the piston absorbs power from the fluid. Due to inertia of the system, the piston moves upwards again. This time, the exhaust valves open and the exhaust is rejected. Again, the suction stroke happens. This cycle, which has a total 4 strokes, is repeated over and over for continuous power production. You may have noticed that a bowl is provided on top of the diesel engine piston. During the compression stroke, this bowl helps produce air that is rapidly swirling. Thus, the injected fuel gets mixed with the air effectively. The mechanical design of IC engines, particularly that of diesel engines, is a challenging and interesting task. Since the combustion process in diesel engines is never uniform and smooth, they are prone to more vibration and noise compared to petrol engines. Thus, diesel engines require a rugged structural design. Out of the 4 strokes, it is only during the power stroke that a tremendous amount of force is exerted on the piston. So a single-cylinder engine will always have high force non-uniformity as shown. Similarly, the output power will also have a fluctuating nature. But with more number of cylinders, one can overcome these problems. Consider this 4-cylinder engine. Here, 4 different strokes can occur at a time. So the power stroke is always present in the engine. As a result, a 4-cylinder engine will have better force and power uniformity. In short, the more cylinders an engine has, the smoother it will operate. A 4-cylinder engine generally operates on the following firing order. A heavy flywheel which acts like a power reservoir further helps in smoothing out non-uniformity of power. A huge unbalanced force arises in the form of dynamic unbalance due to the excessive mass at the connecting rod side. This is negated by providing counterweights on the crank side. Opening and closing of valves are accurately controlled by a pair of camshafts. Camshafts derive motion from the engine. It is clear that the camshafts need to rotate at half the speed of crankshaft. We hope you had a nice introduction on the working of diesel engines. Thank you.
recent trend in robotics is to get lots of robots working together. But parallel operation is not always enough. Some tasks are just too difficult for the robots to solve on their own. So-called self-assembling robots can combine forces by connecting to each other in a broad range of morphologies. But it's hard for the robots to know when to use different morphologies because of their limited local sensing range. The solution? Flying robots. Flying robots can analyse the environment to see what task needs to be solved, what morphology is most appropriate to solve that task, and which robots are best placed to form the morphology. However, it is non-trivial for the flying robot to communicate with specific robots on the ground. The problem is that the robots have very different views of the world, which makes it difficult for them to agree on a common frame of reference. We have developed a method that allows robots to select their communication partners without relying on any kind of global coordinate system. We refer to our method as spatially targeted communication. Let's say a flying robot wants to communicate with a specific robot on the ground. This one, for instance. To start the selection process, the flying robot illuminates its red LEDs. To join the selection process, the robots on the ground light up in blue. In a series of elimination steps, each ground-based robot independently displays a sequence of randomly selected colours. At each step, the flying robot matches the colour of the target robot. Whenever a robot on the ground sees that its own colour doesn't match the flying robot's colour, it eliminates itself. The process continues until only the targeted robot is left. An extended version of this method allows adjacent groups of robots to be selected and then given movement and morphology formation instructions. Here, the flying robot has already targeted the 4 robots closest to the hill and instructed them to form a line morphology. Spatially targeted communication expands the potential of self-assembling systems by allowing ground-based robots to benefit from cooperation with flying robots. Any robotic platform equipped with LEDs and a standard camera can participate in spatially targeted communication.